During AI Day 2022, Ashok Elliswamy and the Full Self-Driving team got into a lot of details about how full self-driving works. Today, I want to look at a little part of that, which is the Occupancy Network, which is really critical not only to the way full self-driving works, but to the way Tesla Bot works, and to the fact that Tesla is now confident enough to get rid of their ultrasonic systems. Let's take a look. Hey y'all, it's Dr. Know-It-All. I'm going to try things a little bit different today. I'm going to try OBS software so I can actually play the video and actually talk about it over the top. So I'm going to play a piece of Tesla's AI Day where they talk specifically about occupancy networks. I'm going to start with Ashok talking about sort of giving a general overview of what occupancy is, and then Phil goes into detail about it, and I'm going to kind of stop the video and talk about it. The actual video is about 7 minutes long. It's a 7-minute portion of the whole video, which is almost 3 hours long. Anyway, it starts at 1 hour and 12 minutes. I, of course, will leave a link to the entire AI Day 2 presentation in the description. You should definitely watch it for sure. The other thing I would suggest is if you haven't watched my explainer about Ashok's talk about occupancy networks, you should probably stop and do that now. I'll put a card up in the corner, but also something in the description and also something at the end of this video. I recommend watching that one first as opposed to watching this one, but certainly if you feel like you know what you're doing or you just want to live dangerously, by all means watch this one first and then you can watch that one second. Anyway, I'm going to start with Ashok's overview of the occupancy network and what it does.
The occupancy network acts as the base geometry layer of the system. This is a multi-camera video neural network that from the images predicts the full physical occupancy of the world around the robot. So anything that's physically present, trees, walls, buildings, cars, balls, what have you, it predicts, if it's physically present, it predicts them along with their future motion.
Okay, so as we will see, what the occupancy network does is basically in his talk, he said that geometry was greater than ontology, which basically means it figures out what's in the scene. In other words, what you're allowed to drive on versus what you're not allowed to drive on. And then it does a kind of a basic semantic level of understanding. It's sort of like road surfaces, things you don't have to pay attention to, like buildings, curbs, parked cars, pedestrians, objects in the road like debris, things like that. So it sort of splits it up into a basic semantic understanding, and it also talks about flow, and we'll talk about that more later on. But the essential idea here is, even if it doesn't know what the heck it is, even if it's just, some object like this, well, it probably doesn't care about a bottle, but, say a large rock or something in the road, if it doesn't know what that object is in the road, it will still avoid it. And that's the primary thing. It's geometry. It's like a volumetric understanding of the world around it in a relatively coarse and crude manner. But that coarse and crude manner allows the car to safely drive around anything without having to first understand what that object is. And that's really, really important for basic safety. All right, and then we get to Phil talking about occupancy networks in some greater detail. So what I'm going to do is play and pause the video and talk about the sections as he goes through them.
Hey guys, my name is Phil. I will share the details of the occupancy network we built over the past year.
Okay, so let's just stop right there. They built this in the past year. This didn't exist a year ago. AI Day #1. This didn't exist. Actually, as it turns out, Ashok later on talks about how this was kind of a pet project of his and how he did most of the coding himself, which is really, really impressive. Anyway, so this is something that Tesla was able to do in a year. That is very impressive in its own right.
Our solution to model the physical world in 3D around our cars. And it is currently not shown in our customer-facing visualization. And what you will see here is the raw network output from our internal dev tool.
Okay, so that's also important. So if you drive full self-driving beta, you do not see the occupancy network. This is something that is an internal thing for testing, although, gosh, it would be awesome to have an option to visualize that as you were driving around. But basically, the visualization that you're going to see in this presentation is something that only developers can see. It's running in every single car that's running full self-driving beta. It's just that you can't see it under normal circumstances. And oh, by the way, I believe that I am the person at the very far left left. So I don't know if you can see my mouse here, but if you take Phil and you sort of draw a line to this sort of gray hair, because I got a lot of gray hair, amongst the dark there, at the very, very edge of the screen on the left-hand side, that I believe is me. So anyway, if you see a lot of nodding, that would be me because I really, really enjoyed this part of the talk. All right, continuing on.
The Occupancy Network takes video streams of all our 8 cameras as input, produces a single unified volumetric occupancy in vector space directly.
Okay, so a couple of things there. It's going to take us forever to get through this. I kind of knew it was going to. But basically, it's converting everything into vector space as opposed to raster space. The important part about that is it's going from a 2D image, right? So what you're watching right now is a 2D image of me. It's not the actual vector space. But in the room where I'm recording this, you could consider me to be in more of a vector space. There's a three-dimensionality to my body. There's a three-dimensionality to the fact that the wall is very far behind me and all the objects. And this object here, you know, has three-dimensionality. I don't, not an advertisement for sparkling water. I just happened to have one here I was drinking earlier. So anyway, it's a full-on three-dimensional vector space. It's not a raster space. And part of the genius of what Tesla's been doing and what Andre Karpathy talked about last year a lot at AI Day is the fact that they're able to convert between raster space and vector space. And it looks like they've actually got that working very, very well, which is super impressive. So if you look at this, you can see that we've got the white indicates, in my mind, elements that are not important to the car. It's just background stuff. So like trees and, you know, curbs, things like that. Well, actually the curbs looks like they're green. So I believe that the curbs are represented as green. Then you've got static objects that are important because you've got the drivable space that the car is on, but there's static objects around it. Those red objects are things that it's like, okay, you have to avoid these. So green is the curb. That's something that you obviously don't want to drive over the curb, but then there's red objects in the scene, which represents these cars, or in this case is cars. And you can see that the vehicle is passing past these vehicles, these other vehicles. It doesn't have to necessarily know what they are in great detail, but it does understand that these cars are dangerous, right? So I guess they're in red because they're dangerous, although probably they just have colors that are assigned to things. But basically, red is bad. Don't hit the red things. Stay away from the white stuff because it's not really part of what you're dealing with. And then don't drive on the green stuff because that's curbs.
Every 3D location around our car, it predicts the probability of that location being occupied or not.
So here we go. We can look at this again. You can see that the road surface, they're now beginning to map out the road surface, which is what you're allowed to be on. You can see that there are occlusions, right? So you can see that the car is not able to see past this vehicle up here. I guess it would be the, I don't know if that's a minivan or whatever, that sort of dark gray colored object. It's blocking things behind it, but it can still go ahead and figure out what's around it. I'm not exactly sure what the brown is. The brown maybe is driveways or something that could potentially become something. Anyway, semantically, it obviously understands that as different, but you can also see that it's starting to map out the road surface as well.
Since it has video context, it is capable of predicting obstacles that are occluded instantaneously.
So again, very important, it's using video. This is not still frame images, it's all video sequences. So it has like some sort of window, maybe a 2-second sliding window of time. So as the car is moving, it's constantly seeing different images of the world. It's like a video sequence. So it's able to map out what's going on and it's able to ignore occlusions. So even if it temporarily can't see something, it can still figure out that it's probably occupied or that it's still there.
For each location, it also produces a set of semantics such as curb, car, pedestrian, and road debris as color-coded here.
Okay, so here you've got a really interesting thing, and Ashok actually presented this in his talk, and I talked at length about this, but you can see that there are these kind of stanchions that they've put down outside of this truck to hold it still so that it, that doesn't not fall over when the cherry picker is up. And so what the vehicle is able to see is, it's like, I don't understand what this is. It's a orangish yellow color. I don't know what it is, but I'm not going to hit it. So that's the important part of all of this, is it's like, it's not going to hit it. This could be the person in this case as well. I'm not exactly sure. Let me watch the video real quick. So it could be that this is a person in addition or instead of that, or it could be these stanchions, but eventually it does see the stanchions. Yeah, I think it's seeing the stanchions here and then the person over to the side. So anyway, so yeah, so this is really, really important that basically it doesn't matter if it understands everything perfectly, it's understanding volumetrically what is occupied, and then the semantics or ontology comes second.
Occupancy flow is also predicted for motion. Since the model is a generalized network, it does not tell static and dynamic objects explicitly. It is able to produce and model the random motions, such as a swerving trainer here.
So, okay, so here we've got one more color, and this color is really, really important. The blue for the occupancy network means that it's moving. So what Ashok has called occupancy flow, which is, again, a video sequence. Your car is moving, let's say at 30 miles an hour or something like that. If another vehicle is moving at approximately that same speed, it's staying still in the frame as opposed to moving past the car, right? Everything that's still in the world is moving past the car backwards. So anything that's moving with the car, because it's a video sequence, it can figure that out. And if it's moving with the car models it as blue, as a moving object. So it's critical for the vehicle to be able to understand occupancy flow. And because it's got video sequences, it's able to then convert that into a video vector space, which is not a still vector space, but a continuously changing vector space. And it's able to take that occupancy and say, these pixels, these voxels in the space are moving with me at some relative velocity. And therefore, I need to model the fact that they are actually moving with me. They're not still. And so you can see, let me see if I can rewind just a little bit, but you can see as the U-Haul trailer, this person swerves and the trailer starts rocking back and forth. You can see how the model here, the blue model, is being modeled back and forth. So the car knows that it needs to kind of squeeze over into this lane to avoid being hit by the trailer.
Explicitly, it is able to produce and model the random motions, such as a swerving trainer here. This network.
So I don't know if you could see that, but the car actually kind of just tucked right around it at the edge. So it was able to move around that vehicle.
It's currently running in all Teslas with FSD computers. And it is incredibly efficient, runs about every 10 milliseconds with our neural net accelerator.
So that is very cool in its own right. So, one of the problems with this is you could probably manage to make this happen. Maybe even as somebody as stupid as I am would be able to make this happen and run at like an hour per frame or something like that. But in order to run this at 100 hertz or every 10 milliseconds, in other words, 100 times a second, it's able to run these calculations and update the state of what's going on. So that's 100 times per second. Again, if you're a video gamer or something, like 60 FPS is very, very smooth motion. So this is faster than a fast video game. It's very, very rapid updates, and that is remarkable.
So how does this work? Let's take a look at the architecture. First, we rectify each camera images with the camera calibration.
Okay, so just really quickly, rectify, what that means is that every camera has a distortion. So if you go out to the edges of the frame here and you look at it, I don't know if you'd be able to, let's see if I can figure out which frame I'm in. Backwards here. So anyway, if you look at the edges here, the likelihood is that the bookshelf, like the straight lines in the bookshelf, are going to be slightly curved because of the fact that my lens is, it's spherical. So it has distortions at the edge. So the first thing you have to do is kind of flatten those images out. So that takes some, a relative amount of work, but it's very important to do that so that you can then stitch them together.
And the images we're showing here were given to the network. It's actually not the typical 8-bit RGB image. As you can see from the first image on top, we're giving the 12-bit raw photon count.
So again, an important point here, and this has already been pointed out as well. We've heard about this before, but we're putting this all in one space now. So these images are not processed images. When I take a picture with my iPhone camera or something, before I see that image, it's processed through a whole bunch of software. What they're doing here is they're taking the raw photon count, the raw input in YUV space, not RGB space, but YUV space. They're taking that in directly, and they're not processing that stuff so that they can get the maximum amount of information out of that image.
The network, since it has 4 bits more information, It has 16 times better dynamic range.
Okay, so basically what happens is a 12-bit image gets reduced to 8 bits when you see it per channel. And what he's saying is you get 16 times more dynamic range because you've got an extra 4 bits of signal. So you've got extra information. It's not processed. You're not losing the time and the compute power to process this stuff. You're just pulling it all straight in. What that means is that they had to redo all of their data when they changed over from this, because originally they were using post-processed images like what a human being would look at. So they had to scrap all of their data and go back and redo it again, which is just super impressive that Tesla is able to do that. So kudos to their data and their auto labeling and their, all of the teams that are working on this.
As well as reduce latency, since we don't have to run ISP in the loop anymore. We use a set of reglets and BiFPNs as a backbone to extract image space features. Next, we construct a set of 3D position query along with the image space features as keys and values fit into an attention module.
Okay, so let's talk about that. So the first thing that you do is the regnets and the BiFPNs are types of neural networks that they are using to sort of pre-process all of this stuff together. So they're taking the regnets and the BiFPNs to put them into a format that they can then feed them into a transformer. So the spatial attention kind of column there is a transformer where they're using QKV to be able to query what's going on in this world space and pay attention to what's important in the scene.
The output of the attention module is high-dimensional spatial features. These spatial features are aligned temporally using vehicle odometry to derive motion.
So now what you can see is from the spatial attention layer, it looks like what they've got is they take their 8 cameras and they combine them into one sort of high dimensional image as he was talking about. So it's not a picture like you would be able to see with your human eyes, but it's this thing, this 360 degree sort of image that they've got, and they can pay attention to whatever they need to within that, the important objects within that. Then what they have to do is they have to temporally align that with other frames in the video sequence. So at this point, what we've got is we've got a single image, but then what's happening is it's aligning those images with other images to create some sort of like 2-second or something like that window of time where it's able to see a video sequence as opposed to still image sequence.
Last, these spatial temporal features go through a set of deconvolution to produce the final occupancy and occupancy flow output.
So then what we get is we get this, as they say, spatiotemporal features. We've got this thing that's in a high dimensional space, but a relatively low resolution, I believe. And so what they're doing is they're deconvolving this, which basically means as opposed to a convolutional neural network that takes a large image and shrinks it down into a high dimensional space, they're doing the opposite. They're deconvolving it. So they're taking this image that's really, really information rich, but a relatively low resolution, and they're deconvolving it back up to a big space. Again, not just a single image, but a video sequence. And then what you get is volumetric outputs. So what we've gone from is 2D, 8 2D inputs, frame at a time, to something that's a video sequence that's 360 degrees, to something that's now a vector space. It's a volume. It's a, sort of a cubic or rectangular cube volume that this thing is sitting in with all of the features around it that it's interested in.
They're formed as fixed size voxel grid, which might not be precise enough for planning and control. In order to get a higher resolution, we also produce per voxel feature maps, which we feed into MLP with 3D spatial point queries to get position and semantics at any arbitrary location.
So I'll move myself over to the other side temporarily here so we can see this stuff over here a little bit better. Anyway, what happens is after you get this volumetric space, you then take the queryable outputs and put them through a multi-layer perceptron, a kind of more traditional type of neural network to get two things. Number one is you get continuous occupancy probability. In other words, all around you, what things are probably occupied versus not occupied. You also get continuous 3D semantics. So it's two separate processes that are running in parallel. And note that you don't have to have semantics in order to have occupancy. So if it can identify what it is, like this is a car, that's great. But if it can't identify it, it can still say this is occupied, even though I have no idea what this thing is.
After knowing the model better, let's take a look at another example. Here we have an articulated bus parked on the right side of the road, highlighted as an L-shaped voxel here. As we approach, the bus starts to move. The front of the car turns blue first, indicating the model predicts the front of bus has a non-zero occupancy flow. And as the bus keeps moving, the entire bus turns blue. And you can also see that the network predicts the precise curvature of the bus. Well, this is a very complicated problem for traditional object detection network, as you have to see whether I'm going to use one cuboid or perhaps two to fit the curvature.
So let's take a real quick moment here to also realize that there is this, I don't know what it is, some sort of chimney or something like that. This is probably in New York City. But anyway, there's some sort of semi-identifiable object in the middle. And note that the car has modeled that very, very well and knows it needs to avoid it. In terms of what Phil is talking about here, he's talking about this bus, which obviously is one of those ones with a connector in the middle. The beginning of it starts to move, so it turns blue, and then the back gets pulled along. So both of them turn blue, and it's able to understand that area is now not only occupied, so the car can't go there, but occupied and moving, so the car can slow down and then it can continue after the bus and go around this pipe or whatever this thing is that's sticking up in the middle of the road. So it's able, again, even if it doesn't understand exactly everything that's going on, it's able to model that. And what Phil was talking about with traditional sort of scene segmentation sets, you would actually create a box around the bus, and it would be very complicated because suddenly the system would break down because it would say, wait, there's a box around the bus and another box, and are these two boxes connected, and I don't understand what's going on. Very easy for the neural network or for the machine learning system to break under those circumstances, whereas here, if you're kind of using the raw information and creating a raw occupancy network, even if it doesn't know what it is, it can tell that it's there and that it's moving, and that's all it needs to be able to do to avoid hitting it.
But for our occupancy network, since all we care about is the occupancy in the visible space, and we'll be able to model the curvature precisely. Besides the voxel grid, the occupancy network also produces a drivable surface. The drivable surface has both 3D geometry and semantics. They are very useful for control, especially on hilly and curvy roads.
So again, notice what we've done is we've parallelized things. Out of that deconvolutional layer, we've now spit out a surface outputs as well, which means the road surface. So not only is it understanding the geometry, it also understands the semantics of the road surface. In other words, it has ideas about what's going on the road surface. I'm not sure if that's only things like lines and stuff like that, like if there's a right turn arrow or something along those lines, or whether it's the actual curvature, three-dimensional curvature of that space. So it could be either one of those. I'm not exactly sure from the talk, but in any case, we've got a drivable surface that's just, again, geometry, and then we've got a semantics layer that's running in parallel with that.
The surface and the voxel grid are not predicted independently. Instead, the voxel grid actually aligns with the surface implicitly. Here, we're at a hill crest where you can see the 3D geometry of the surface being predicted nicely. Planner can use this information to decide perhaps we need to slow down more for the hill crest. And as you can also see, the voxel grid aligns with the surface consistently.
So again, this is amazing stuff. You've got an area that the car simply can't see. It's over the top of the hill, and a driver can't see that either. But what it's able to do is make predictions, and it's able to use the occupancy of the area around it and the alignment of that occupancy with the road surface to be able to make predictions about what the road surface is going to look like, and also to decide that it wants to slow down if it's not exactly sure what's over the top of this hill crest. So these are all really, really impressive. The fact that the road surface and the voxels around the road surface are aligned with each other is really, really impressive. That's not a simple task at all, I'm sure.
Down more for the hill crest. And as you can also see, the voxel grid aligns with the surface consistently. Besides the voxels and the surface, we're also very excited about the recent breakthrough in neural radiance field, or NeRF. We're looking into both incorporate some of the nice NeRF features into occupancy network training, as well as using our network output as the input state for NeRF. As a matter of fact, Ashok is very excited about this. This has been his personal weekend project for a while.
So I covered NeRFs, or neural radiance fields, in more detail in my Ashok talk explainer video, which again you should watch. But basically what it does is it's able to sort of raycast into a scene and recreate a three-dimensional scene from multiple 2D images. So basically it's recreating 3D space out of 2D images. And what they're able to do with these NeRF renders is they're able to create a ground truth to check against what they're doing and to be able to see if their predictions in the voxel in the occupancy network space are actually correct. So it's really, really critical that they're using this as well to create a quasi ground truth to sort of check up on the occupancy network and make sure it's working in a more automated fashion instead of having to have human beings, in the loop at every point, which would be unconscionably slow.
These NeRFs, because I think the academia is building a lot of these foundation models for language using like tons of large data sets for language. But I think for vision, NeRFs are going to provide the foundation models for computer vision because they are grounded in geometry, and geometry gives us a nice way to supervise these networks and frees us of the requirement to define an ontology. And the supervision is essentially free because you just have to differentially render these images. So I think in the future, this occupancy network idea where images come in and then the network produces a consistent volumetric representation of the scene that can then be differentially rendered into any image that was observed, I personally think is a future of computer vision. And we do some initial work on it right now, but I think in the future, both at Tesla and in the academia, we will see that these combination of one-shot prediction of full volumetric occupancy will be the future. That's my personal bet.
So this gets a little esoteric, but it's kind of going off of what I was saying. It's creating a ground truth thing that you can actually check against. So you can actually create occupancy networks, and then you can create NeRFs as a separate output of this, and you can check them against each other. And that's essentially a way for AI to bootstrap itself and to learn how to do things without human beings having to be involved at all. So this is very cool. And this is also the part that Ashok, as he was saying, was working on as a weekend project. It's pretty amazing when these guys are just like, yeah, I'll just work on NeRFs as my weekend project. It's way above the head of most of us to even understand what they're working on, much less be able to do it.
So here's an example early result of a 3D reconstruction from our fleet data. Instead of focusing on getting perfect RGB reprojection in image space, our primary goal here is to accurately represent the world in 3D space for driving. And we want to do this for all our fleet data all over the world in all weather and lighting conditions. And obviously, this is a very challenging problem, and we're looking for you guys to help. Finally, the occupancy network is trained with large auto-label dataset without any human in the loop.
And that brings us to data and auto-labeling, which is the topic for another video. So let me rewind here for a second and let me go out to a little bit broader picture to help you understand what's going on right now. But I also want to talk about the future because the future is way, way brighter than what they talked about in this particular presentation. So first, let's talk about this adorable little guy here. It's a kind of a teddy bear with a VR headset on, I guess, or something. He is represented in voxels. And so what you can see is the entire, teddy bear looking thing has been divided up into tiny little cubes that define the object. And basically it's saying, is this space occupied or not? If it's not, it's just white as a background. If it's occupied, it's one of these colored little cubes. So this is really beautiful. And this is the way that you can create a scene in 3 dimensions and volumetrically explain what's going on. The problem with this is that you either have to have very, very tiny voxels in order to get all the detail, or you sacrifice detail. So you can see an area like this, like his headphones that are very flat, or else the front of the VR screen. Those are flat. Those could be defined in just a couple of voxels. They could be much, much larger. But if you do that, you're going to lose all the detail of the fingers and the toes and everything. And even so, you're still losing a lot of detail on these very sharp edges. So the areas where there's a lot of curvature, you're losing a lot of detail, and you can definitely tell that this is a voxel representation, not an actual continuous representation. In an analogy, like in a 2D picture, if you zoom too far in on like a JPEG, you see that it starts to get aliased. It's stair steps. This is the exact same thing in the 3D world. You could call it 3D aliasing. All right, so now let's jump back to this point in the presentation because this is important also. So you can see that the world is represented in voxels, and the person I talked to who's in the know after this presentation, I asked a bunch of questions. So this information comes from somebody who really knows his stuff and would be accurate about what's happening right now and what's going to go on in the future. I'm not going to say his name just in case it would cause a problem. But anyway, currently these voxels are 30 centimeters on a side approximately. And you can see some of them are only half full, right? So it's like half the voxel is full and half the voxel isn't. But basically 30 centimeters is a pretty big chunk, and maybe about this, So it's fine for a car for driving and for not hitting something, but it's problematic because even at 30 centimeters per cube, this space is very large. And the person I talked to said that what you have currently is 120 meters. And I believe what that's broken up into is 20 meters behind the car and then 100 meters in front of the vehicle. So what that means is you've got a cube, and I don't know how tall it is. It's, maybe 10 or 20 meters tall. It's probably not that tall. In fact, it's probably not very tall at all. It looks like it may only be about 5 meters tall because you can see that the buildings are cut off. They're not represented up to their full height. So anyway, but what you've got is you've got about 20 meters behind you, which would be about 20 paces as you're walking, and then 100 in front of you, which would be like a football pitch, whether it's American football or soccer, it doesn't matter. It's, approximately 100 yards, 100 meters you can see in front of you, which is absolutely fine for city driving, but not so good for highway driving, because highway driving, you can cover 100 meters relatively quickly if you're going 120 or 30 kilometers an hour. So that's a significant problem. And it's one of the reasons I believe that full self-driving beta at high speeds is a little bit tweaky. It kind of breaks late and everything, because I think it's not seeing things out far enough yet. So what is it possible to do about this issue in order to save compute time in terms of being able to see longer distances so you can drive more safely at high speeds? Well, you can use a trick that games have been using for a long time, which is called level of detail. So what you can see is, the further away you get from objects, the lower the level of detail is. So I'm sure you've all played computer games where if you're up close, you get, level of detail 3 or 4 or something, where you have lots and lots of detail about an object, a person, a house, or something like that. As you move backwards, you get to a lower level of detail. And then as you move further away, you get to a lower level of detail. And finally, in the background, you just get kind of big giant cubes that represent the space that's around you, but they're really far away, and they're texture mapped with like building looking stuff on them. So you don't really notice. And then they put some haze in and stuff like that, so you can't see. But this is what games have been using for years and years and years, is this very discrete level of detail thing. So the first 10 or 15 meters, you have high level of detail. The next 30 meters or so, you have a medium level of detail. The next 100 meters, you have kind of a low level of detail. And then after that, you have super low level of detail. So you have this, and it's broken up like this. But wouldn't it be better if we had continuously varying levels of detail? And what we get here is something from a research paper that I found. This is a kind of a nice image of this. There's a cow here, and consider the cow the camera. And what you can see is that you've got level of detail that's very high here, but as it moves backwards away from it, the voxels get bigger and bigger as you move away from the cow or the camera. So it could start off at like 1 centimeter cubes, and as it moves backwards, it goes to 5 centimeter cubes, and then to 10 centimeter cubes, and then to 30 centimeter cubes, and meter cubes, and 10 meter cubes, so that you can see all the way from the foreground all the way to the sky in the background, infinite horizon away, because you can model the infinite horizon as basically 1 or 2 giant cubes, right? So it takes very little processing power. This is pretty ingenious. And again, the person I was talking to said this is coming very soon. And in fact, this ties into my video from yesterday, which was why I said to stay tuned, because I believe that the reason Tesla feels they can get rid of the ultrasonic sensors is precisely because they're able to do this continuously varying level of detail. Because up close, they're now able to get super high detail. It's no longer 30 centimeters on a side. It's no longer these big cubes like this. They're able to get like centimeter on a side cubes. So you can go at very slow speed and get really close to objects and avoid them at just the right amount, right? So it can warn you that you're getting within like 10 or 15 centimeters of something, and you better stop right now. And this is the enabling technology for that. So what I'm seeing is that this continuously varying level of detail, going from really tiny voxels in the foreground all the way up to giant voxels in the background, is what is going to allow this. And it's basically going to allow the computer order to be able to see the infinite horizon. It will no longer be cut off at 100 meters in front of it. It will be able to see forever, but at the same time, super high resolution in the near ground. And if you think about it, that's the way we human beings see as well, right? We don't see the sky in all of its infinite detail, like every single pixel. We just see a big blob of sky. We're just like, hey, blue, you know, in the background. But up close, we really concentrate on things and we can see high levels of detail in the foreground and less detail as we move away. So it's the way the human eye sees. Again, what you're getting is that sort of biological inspiration where you're seeing that the way that the human neural network works and the cameras and all of that kind of stuff. What they're doing is they're mimicking that in the computer realm, and they're doing this all in hardware and software. That's super impressive. All right, so this was a very long and a very geeky episode, but I hope you all enjoyed it. This is just amazing stuff that they're working on. I'm super excited for the state of the art where they are right now and what they showed us in the presentation, but I'm even more like way excited in what's coming in the next or the following software revision. This is going to be a massive upgrade if they're able to go from just being able to see at 30 centimeters on a side resolution to suddenly having an occupancy network that has essentially infinite resolution, super fine detail close up, you know, bigger and bigger detail as you go further away, and it doesn't matter so much, and you've got time to be able to figure that all out. So anyway, this is incredibly exciting news. This is amazing that they're able to get rid of ultrasonics, and again, I think that the occupancy network changes that they're working on is the reason they can get rid of ultrasonics. So all of this stuff ties together, and it just shows how radical Tesla really is and the progress that they're making. And I hope you all agree with me about that. All right, I hope you enjoyed this episode and found it fun and interesting and thought-provoking and quite geeky. If you did, please do like it so other geeks can find it. And of course, consider subscribing for more of this kind of content. As always, a huge shout out to my patrons on Patreon. Thank you all so much. I really appreciate the support, you know, the financial support to be able to get out to California and go to these kinds of events, but also just, you know, the emotional support and the talking about really cool topics and everything. I really do appreciate it. Thank you so much. And of course, if you want to join the team, just check out the link in the description. And if you're interested in a whole bunch of really cool merch, check out our merch store. Link is in the description. We have TeslaBot t-shirts, the Tesla meme t-shirt, success is a possible outcome, 4680 battery cells. All of that stuff is on t-shirts, mugs, tumblers, and on. So check it out. And for those of you interested in investing, check out WeBull, an amazing platform for buying and selling stocks, and now cryptocurrencies like Bitcoin, Dogecoin, and others. Open an account and get a free stock valued at up to $200, and fund your account and get another free stock valued at up to $1,600. Check out the link in the description and help the channel at the same time. Thank you. And finally, don't forget we are both Tesla and Amazon affiliates. If you look in the description, you can see how going shopping for a solar roof, a Powerwall, or anything on Amazon helps out the channel. In the meantime, I'll see you in the next one. Bye-bye.